Geoscientists, this is video number 2 for the statistical analysis using Excel for peak streamflow data in which we are calculating the recurrence interval and the annual exceedance probability. So in the previous video, I walked you through how to download the data and how to calculate from a particular stream gauging station and how to calculate recurrence interval and probability. And now we are ready to make our graphs. And once we do that, then we can actually determine graphically the 100-year flood limit for this stream measured at this location. So the first thing I want to do is graph the recurrence interval versus the stage. The default system for Excel is to, when it makes a graph, the first column you highlight will be the X column. So to get around that, I'm going to copy my stage column. I'm just going to highlight the whole column and hit Control-C or copy. And I'm going to paste it over here. So I've just repeated this column, and that's going to mean that when I highlight a column to the left, that's automatically going to go into the X column because we want stage to be our Y column. So let's highlight these. We'll give them a little color so we can see them a little bit better. And I'll make it bold too. So these are now the columns in our spreadsheet that we're interested in. First thing we want to do is graph recurrence interval versus stage. So I'm going to highlight column G, and I'm going to hit Control on my computer or PC in column I. So I've just highlighted those two columns, and then I'm going to come to Insert, Chart, and I chose a scatter chart. So now this shows a funny looking graph like this. Let me make it a little bit bigger so we can see it better. So the Y column here, the vertical axis, is our stage, and the X-axis, which is automatically always the left, the column that you highlighted to the left, the first one, is recurrence interval. I need to give my axes some titles. So I'm going to click on this plus here and format the graph here a little bit. So we're going to give it a name of recurrence interval in years. There's the name of our graph. Axis title, I'm going to say stage. Feet. Actually, the graph, I'm going to actually specify the stream name. So this is going to be Mill Creek. You could put in Duck Creek for yours. So the y-axis in this case is stage. The x-axis is recurrence interval. In years. Now, you should see a graph that in recurrence interval, you should see a graph that goes from basically 0 on the left to a much larger number on the right, and the stage should be the range of stages that you have in your data set. And so you should see a scatter plot that goes from a low number with a nice smooth curve that goes up to a high number. If you don't have a graph that looks something like this, you did something wrong. You need to go back. You've got it. You've got the wrong data chosen, or you've got the columns reversed, or something like that. All right. So now, how do we get to the 100-year flood level? Because notice we only have a data set of 81 years, right? So how do we predict the 100-year flood limit with 81 years? So the standard procedure here is to change your x-axis here so that it is not an arithmetic scale, but you want to change it to a log scale. So I'm going to choose my x-axis. I'm going to just click on the x-axis, and that should pop up a format axis window over here, and I'm going to change it to a logarithmic scale. And now we go from 1 foot to 10 feet in the first half of the graph, and then 10 feet to 100 feet in the second half of the graph. Now I'm going to do one more thing here just to make it easier for us to see. If I do a right button click, I can click on Add Minor Grid Lines, and I'm going to do a right button click again, and I want to format the minor grid lines because for some reason it automatically doesn't give those much color. They're there, but they're really hard to see. So I'm going to choose a color for my minor grid lines that I can actually see. I'll put in black, and now I can actually see we go from 1 to 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 20, 30, 40, 50, 60, 70, 80, 90, 100 on our logarithmic scale. Now, this is really cool because now we can easily extend this graph because it's almost a linear trend, and you're going to print this out and you're going to physically extend the graph out to 100. And so where this line, let's see if I can do that. Where this line, basically, you're going to fit a line to it, and there's a little bit of interpretation here. Something like that. You can print this out and do this, and you might only do it for the second half of the data. Now we've got pretty nice linear trend, and you can extend it out to the maximum range here at your 100-year recurrence interval. What that means is that for Mill Creek at this location, our 100-year recurrence interval is about 12 feet, our stage. That means that that stage of 12 feet should occur statistically once every 100 years. Notice that it's higher than any other points here. So once every 100 years, we should have a flood that exceeds that stage of 12 feet. That also means that it has this 12-foot stage has a 1% chance of being exceeded in any given year. So there is the recurrence interval graph. Now we're going to make a second graph that's very similar to that of the exceedance probability. So you're going to highlight column H and column I, and you're going to do the same thing. You're going to click Insert and choose a scatter plot here, just like this. And it's going to look, sorry, move some things around, choose your graph. It's going to look really, really similar. You can make it a little bit bigger here. And then we're going to do the same things here. We're going to hit the plus button and make sure that we've got a place to put axis titles and a title for our graph. So the title for our graph here is going to be Mill Creek. You'll be putting in Duck Creek. And this will be annual exceedance probability in percentage. You should see that the graph goes from higher to lower, and it should be a pretty straight line. You should see a nice relationship there. And it'll look really similar to the other graph, but flipped upside down, sort of. And now, let's give it titles. So our y-axis title, again, is going to be in stage, in feet. And our x-axis title is annual exceedance probability. In percent. There we go. Now we're going to do the same thing. We are going to change the x-axis to a logarithmic scale. So highlight the x-axis, should pop up a window for the format axis, and we want to change it to a log scale. Oops, I lost my way here. Oh, I know. I wanted to do a right button click. Format axis. There it goes. And now it would pop up. I could have found my way. choose a logarithmic scale, and that should look something like that. And then we're going to do the same thing that do a right button click, add minor grid lines, and do another right button click, format your minor grid lines, and you can change the color of those to something that you can see, and that's going to help us interpret the graph a little bit more. And so now what we see is we can do the same game here, that we can draw a line. So you can print out both of these graphs that you have made, and you're going to draw a line from a straight portion of your curve on the logarithmic scale that you think is a pretty good extension of that, and from that you can calculate the annual exceedance probability and where that's going to be at 1%. So remember, 1% annual exceedance probability would be our 100-year flood limit. So again, it's basically at 12 feet for us here. So you should get the same results there. So these graphs basically look very similar, but they're flipped. So there we've done it. We have figured out how the 100-year flood limit is calculated from a data set that is less than 100 years. All we need is a fairly good data set. You could theoretically do it with just 5 or 6 years of data. The more data you have, the more years of data you have, the more accurate your predictions are going to be. Again, there are some assumptions with this, because it's assuming that the drainage basin doesn't change much over that time, and that the precipitation patterns, the weather patterns, don't change very much over that time. And that's something I want you to be thinking about in your lab exercises. So you'll be printing out your graphs and your spreadsheet and turning those in with your lab assignment.